Alright, I think we'll get started. Alright, hello everyone and welcome back, I guess welcome back to programming challenges. It has been a while actually. We haven't really looked in, or we haven't done many challenges since September, I want to say. But it just has been a while. Okay, so let me put that, I don't need this. Alright. Sorry, so today we are going to be doing a programming challenge in C. Let me just make sure that this is all transmitting properly. Alright, we're looking good. So we're going to be looking at C today, and we'll be doing generic type lists. So in C, you know that we don't have access to C++ classes, or any object-oriented stuff for that matter. And we also don't have templates. So it's not, we can't say something like template type name t, and then struct list node, and then have a t value. This just doesn't work because templates do not exist in the language C. But what we can do is we can accomplish something similar through a little more of a memory intensive, or not memory intensive, but more conceptual per se way, which is going to be through void pointers. So instead of having a template, we'll have just a void pointer, and that's kind of somewhat how Java works and somewhat how C++'s vectors work. And I'll talk about Java for a second, because in our lists in Java, if we have, the lists are made of classes, but in Java classes in the code are all references. So you're going to have a list of references, which in C and C++ are just pointers. So therefore, it will just be a list of pointers. That's what we're going to have here. Except the void pointer, you can kind of have any sort of thing, because a pointer is just a type. An integer pointer is technically the same as a void pointer, because they just both represent addresses in memory. It's the only difference is when you dereference that pointer, what happens to it. And also with pointer arithmetic, it will add the size of the pointer, or the size of the element that it's pointing to. If you say the pointer value +1 or something like that. So we'll look at two ways to do this. The first will be with dynamically sized arrays, which are like Java array list and the C++ vector. And then we will also be looking at what is this? Hold on. I'm seeing something on my screen and I don't know if this is legitimate. Give me 2 seconds. It could be. What was that? I saw the subscription thing pop up, but I don't know if that was. I have no clue. Honestly, zero clue what just happened, but I don't ask me, but okay. So yeah, we'll be looking at array lists first, where essentially you just have an array and you can increase the capacity of the array by allocating new values, and this array list, this dynamically sized array, will be the best for most purposes. Linked lists are more of a thought experiment, but they are very useful in some cases when you don't want to have as large of a collection, and we'll see why. So we'll talk about dynamically sized arrays first. You essentially start off with some capacity, which is just how many available slots are in the array. And then you have a size, which represents how many slots are currently active in the array. So every time we will add one to the size, and if need be, we will resize the array by allocating new memory and copying the elements over, and then that will correspondingly change the capacity too. So we will just look at that right now. So I need to create my batch files here. That. I forget actually what the specific language is for there, what the specific command is for the GCC running. Oops. What? Ready to choose stop. God damn it. Alright. I should have prepared this before, but we'll just do the run file for now, and if we need to debug it, we will do that. So we'll start with our just hello world. And then run it. No, oops. Is something happen? Alright, good. All works. Alright, so we'll have a header file called, we'll call it dynamicarray.h and dynamicarray.c. Alright, so for dynamicarray.h, we're essentially going to represent this with a structure, because that's what all custom types per se in C are, because remember we don't have access to classes. So we'll do type def struct, and then I'll leave the body empty for now, and then we'll call it dynamic array. And what this is going to be now is we'll have an unsigned integer for the size, so how many elements are in the array. Then an unsigned integer capacity, so how many elements can be stored, and then we will actually have the list. So since we're going to be having an array of void pointers, it will be void ** list. So once again, this is just an array of void pointers. Okay, so we will have our first function, which will just return dynamic array, and we'll call it allocate, and we'll pass in a capacity. Alright, we'll copy this over to dynamicArray.c. We have to include dynamicArray.h. And then in allocate, what we will say is we'll have dynamic array ret that will set up with the memory for the two integers and then the first pointer here. And then we now need to actually set up the memory. So ret dot list is equal to malloc and then we'll say capacity times size of void pointer. And then we also have to set the capacity here. So ret.capacity is equal to capacity, and then return ret. So that should give us a list with a certain amount of elements. And then let's have a default allocation method that will just allocate, let's say 4. So this is going to be called default allocate, and it will just call allocate with the argument 4. So return allocate with 4. Alright, so in main.c, we want to include dynamic array.h, and then I will say dynamic array list is equal to allocate 5, and then we'll print out %d list.size, and then also the capacity. Okay. Undefined reference to allocate. Oh, because that's right, I need to add dynamic array.c to the build path. This is the one downside to working outside of an IDE. What? Oh, right. I need to include standard lib in dynamic array. Oops. Or in dynamic. Yeah. Oh, and then I also forgot my macros. That's a rookie mistake. Yeah, just make sure you have your if not defined dynamic array in the header, and then define dynamic array, and then end if. Okay, I guess we need to explicitly set the value to 0. What we should actually do for the capacity is if this was not able to allocate anything, we can just set the capacity to 0. So ret.capacity is equal to ret.list as a boolean, then question mark, capacity, and then :0. So if ret.list returns something, then this pointer will resolve to true. Otherwise, it's going to resolve to false, and it will give us 0. Okay, let's do what functions do we actually have with a dynamic array? Let's do add first. So void add will pass in a dynamic array pointer list, and then a void pointer element. Just thinking that this is going to be a little weird with void pointers here. Yeah, this is... Yeah, this is going to be a little weird here. I'm going to think about this for half a second. Because if we just have add and then a void pointer, you can't just say add 5. Because 5 is an integer, and you can't take the reference of 5 unless you make it a variable. But if you were to, say, pass this list into another method, and that method had an integer 5 as in a variable, and then we added the reference to that 5, and then once we exited the method, the 5 would no longer be referenced, so it would be a garbage value. So I'm just thinking here. Damn, this is... I'm gonna check something out real quick. Ooh, what just happened? Just trying to read something here. Give me a second. God damn it, this is, I was thinking that this was going to be a breeze, but, and I guess we'll just do it like this for now. Because the kind of way that I'm thinking about using this would be with structures. So that would, let me experiment with this once we actually write the method. So we're also going to have a helper method resize here that will take a dynamic array pointer list, and in resize, so I'll actually just copy the two signatures. So add will just technically just essentially add it at the end. So we're going to say if list.size, so if the number of elements currently is equal to list.capacity, we're going to call resize when passing the list. The reason why is because if the current number of elements is equal to the number of spots in the array and we want to add one, we need to resize it since there are no more spots. And then once we have resized it, the capacity is updated, so we can just say list.element, so list.list at list.size, which is the new, or which it will be the next element, the tail, is equal to element. And then we want to say list.size plus plus. Why is it not right? And then that should be good on that end. Yeah, okay. And then for resize, we're going to have to do something a little weird here. So we're going to create a new void pointer array, new list, and this is going to equal malloc list.capacity times 2. So we'll essentially just multiply the size by 2 every time we resize. And then that times the size of a void pointer. And then we want to copy elements over. So for unsigned int I is equal to 0, I is less than list dot size I plus plus, then new list at I is equal to list dot list at I. So we're just taking the elements from the current list and we're just moving them over. And then we want to say list dot list is equal to new list. and then list.capacity times equals 2 or left shift equals 2. This should actually be a left shift equals by 1 because we only want to shift it over by 1. Okay, let's try this out. So main.c, allocate 4. Now I will, I'll have a character right here. And we'll just have A, B, C, and D. And then we'll have, or let's actually have E, F. And then for the add function, we'll have list, or a reference to list. And then the element will be, we have to have a for loop actually here. So I from 0 to 5, inclusive, or 0 to 6, non-inclusive. And then we can just say add, pass in a reference to list, and then using pointer arithmetic, we can say array plus I, or R plus I, sorry. This returns a pointer, and I is an integer, so we're essentially just moving I slots over from the pointer, which is the character array, the first element. And then I'll actually set up a debug batch file too. Okay. So we will see less and then debug. Break, we'll say 15. Run. Print I. Continue. That's 1, 2, 3, 4. So this should actually increase the size. So let me here print list dot size, which is 4, print list dot capacity. Now let me step into the function. So I'll resize that. Go the next line over. So let me do this. So print list dot list, or I need to dereference it first. List dot list at 0. Attempt to dereference a generic pointer. Oh, I need to dereference. Ooh, what do I want to dereference here? I need to dereference the character pointer here. Alright, good. So I convert the element, so just for this print statement here, I converted the element at 0 to a character pointer, which you can do since it's a pointer, and then I dereference that pointer and I get an A. Should be good. Alright, next. Now I do the same thing, so print dereference character pointer, list.list at 4. E. Perfect. Oop, shit. Alright, so that looks good on that end. But just note that you won't be able to like pass in just an A here. Like the character A. Because it's not a... I mean, it's not giving me any... Ooh, this might actually be interesting. You know what, we'll try that after. But let me just print out... Let me add a print method here. Void print list, and we'll pass in just a dynamic array pointer list. This will simply be, ooh, this, this is gonna be, god damn it, there's a lot of tricky shit here. Yeah, using void pointers is not too fun. So we're gonna have to create a macro function, it's looking like here. Because we're gonna have to pass in a type to convert it to and then dereference. Alright, let me... God, this is not great. This is not fun. Alright, let me... I'm gonna try and find one of my repositories here that has something like this that I've looked at. Preprocessors. Are we actually, haven't we... Haven't we done this? Something like this with where we pass in our, I think that was in the C mathematics stuff. Which, you know, I'm not gonna worry about that right now. I'm just gonna have a print method for the characters here. So it'll only be specific to characters. So void print char list dynamic array pointer list. So printf curly braces for unsigned int I is equal to 0, I is less than list dot size I plus plus. Then printf %c comma space, and then we want to do the dereference, and then in two sets of parentheses character pointer of list at I. Should be good. Oh, it doesn't like this. No, it's good. And then at the end we'll print a closing bracket. And a new line. Alright, let's test this running method out. Or this, our A, B, C, D, E, F. Not bad, not bad. Now let me try passing in the A character. I don't know if that was this was actually gonna work. Okay, yeah, it didn't like it. Alright, perfect. Just making sure. So yeah, the one limitation here is that you cannot pass value. This has to be passed by pointer or by reference. And you cannot pass any values into this. Alright, let's do the... There's, how many more methods? There's insert, and then, you know, let's do remove, actually. So void remove, pass in a dynamic array pointer list, and then unsigned int idx. And then for here, we're going to have a boundary check. So if idx is, or let's actually return a void pointer, because then we can return the element that was removed, which is kind of standard for a list. So if idx is greater than or equal to list dot size, return null, and otherwise we have to left shift the elements, or get the element to be removed. So void pointer ret is equal to list.list at idx, and then void, or sorry, then we need to left shift the elements. So for unsigned int I is equal to idx plus 1. So we want to essentially, if we look at this image here, and we were to remove the 1 right here, then we would essentially have to take the 3, so the next one over, move it left to the 1, and then also the 8 left over to the 3. So we're going to go move from the left to the right and left shift each element by 1. So I is equal to idx plus 1. I is less than list.size and I++. And then what we can, or we can also do this yet another way, but this seems simpler. Then what we're going to want to say is list.list at I minus 1 is equal to list.list at I. Just like that. Now let's test this out. So remove, pass in a reference to list, and we'll remove the element at index 2, so the C. And then print char list, and then a reference to list. Didn't like this. Oh, I need to rename it. There was a naming conflict. So remove list. Or remove at idx. That's better. Oh, yeah, so the one thing I did forget to do was set the last element to null, and then decrease the size. Forgot that. So list.list at list.size minus 1 is equal to null, and then just list.size minus minus. Now if we run it, there should be no F at the end, or there isn't a double F, so that's good. Alright, perfect. Let's also do just get, because that's a pretty simple one. So returns a void pointer get, pass in the list pointer, and then the index. Alright, we'll start off with a similar bounds check. So if idx is greater than or equal to list.size, return null. Otherwise return list, or we can actually just do this in a ternary operator. So return idx is greater than or equal to list.size, question mark, if it is null, colon, list.list at idx. And that will definitely work. Alright, I do want to test something out now. So I'm going to go into main.c and I'm going to try adding in a new method void add test, and we'll create a character c is equal to g, and then we want to pass in the list here. So dynamic array pointer list, and list or add pass in the list and then a reference to c. And then we're gonna just try doing the add test. So what I'm trying to get at here is this character c is a value function, or is a value in the in this function here. So I'm not sure if it will carry back over. Could be wrong though. Yeah, it's not getting anything there because it's trying to find a pointer, a reference to c, but c does not exist. So this is let me try saying character pointer c is equal to malloc1, just for 1 byte, and then dereference of c is equal to a, or g. Now let me run this. Okay, now it likes it. And the reason why it's different is because we explicitly allocate the memory here, but we never free it, which is another function that we have to implement, just freeing up the memory. But yeah, this is going to get a little tricky, I'd say. The way that if you were to use this list outside of here, it would be a little tricky, because you'd have to be super careful about when you pass it into functions and what you can actually set up. And what we actually have to do is, I forgot to do this, but in resize, we actually have to free up the memory that is currently located at the list. So so before we set list.list to new list, we have to say free list.list here. Like this. And then, because there's still memory in that array there, and because we explicitly allocated that using malloc ourselves, that memory will still exist and it won't be freed until the program ends. So now we tell it to explicitly deallocate it, that memory will be thrown away, and it will be allowed to allocate it to other tasks. And then I said we would do a void free list, pass in a dynamic array pointer list. The one thing I don't know is if we want to free all the elements. So how about this? Let's have a method for freeing the list, which will simply just delete the array. However, we will also have a method free list deep, dynamic array pointer list. When we're talking about list functions, if you deep usually refers to, okay, I'm gonna do the operation on the general list, but I will also go into each of the list's elements. So for this case, we're going to free both the list's pointer to the first element in its array, but then also we're going to free the memory at each pointer. So each element will have its memory freed up. So for free list, it's simply going to be just free list dot list, and then list dot size is equal to 0, and list dot capacity is equal to 0. And then for free list deep, it's going to be similar. So free list dot list, but then before resetting the sizes, we have to go into the loop. So for unsigned int I is equal to 0, I is less than list dot size I plus plus. We're going to say free list dot list at I, and then list dot size is equal to 0, and list dot capacity is equal to 0. So now this will allow us to explicitly release the memory that we allocated here. Okay, so then we can also just call that at the end, so free list has reference to list. Okay, so there are a few other functions that we could implement for a dynamic array list. Something like insert, where you insert elements at a specific index, and all you would have to do there is just right shift elements and resize if necessary. But I mean, I think, yeah, there's also set, which is pretty simple. But this captures most of it. I'll probably add those later on, but it's not too valuable, I'd say. Okay. Now on to linked lists. So there are two types of linked lists that we'll look at. There's a single linked list and a double linked list. We'll be doing double linked lists just because of an optimization that it provides. But you should see why dynamically sized lists are often preferred, just due to memory usage and then also runtime. I'm just going to refill my water real quick. Alright, so let's, we'll be doing a doubly linked list. Singly linked list, most of the concepts are the same, except you don't have to actually update as many pointers. So what, we're going to have another header and source file here. So I'm just going to clear the existing code that we have right now in the main file, only in the main file. Keep everything else though. And then for include, or no, actually we can leave it, but yeah. But that, since these we're gonna have to change these memory or these function names just because they're pretty general. So add. So I will actually just precede all the function names with dynarr and then underscore. And the reason why I'm doing that is because that's just telling it, it's the closest to object-oriented programming that we can get. And then the same thing needs to happen in the source file. What's this? Return type does not. Yeah, it does. That's wrong. Alright, so we'll have two more files here. And I'll just call it dlinkedlist.h and dlinkedlist.c. And then, before I forget, I'm going to add them to the build path. So for the header, we have to have our macros first. So if not defined, dlinked list h, define dlinked list h and if. Alright, then we'll have a structure for a node. So now with dynamic lists, you had each kind of, or we're gonna have to have two structures here actually. With the dynamic list, you just had one structure, because you just had the array, and that represented all your elements. However, with the doubly linked list, you're going to have a structure for each node, because each node has a value and then references to the next and also previous elements. Yeah, so I guess I didn't really explain it, but linked lists essentially are lists where each node each node is linked together by a reference. So each node points to the next one essentially in the singly linked list. And then in a double linked list, each node points to both the next and the previous node. So we'll have a struct here, or type def actually. Type def struct, open curly braces, and then at the end of the curly braces, we're going to say dlinked list. Or we actually have to do the node first. So dnode, then type def struct dlinked list. So for the node, we're going to have a void pointer value. Notice now how it's just a single pointer because it's not an array. It stores the value in each node. There's one value per node. And then we're going to have a ooh, this is going to be weird. Dnode, is that a thing? Alright, yeah, dnode pointer next, and dnode pointer previous. Don't know if it's going to like this, because it doesn't know what dnode is yet until it gets to there. And then for the linked list, we're only going to have a reference to a head, so we'll have an unsigned int size first. Then dnode pointer head and dnode pointer tail. It is possible to remove or just to implement everything with just a node structure, but this makes it a lot simpler to do. Okay. So what do I want to have here? So I guess we'll have first. we can just have an allocation method here. So return delinked list, delink or delist underscore allocate. And for this allocation, what we'll say is, well, for the source file, we first have to include a few things. So include delinked list .h, and then we also have to include standard lib. Then the function signature, so the allocation method, we're going to have a delinked list ret, then ret.size is equal to 0, ret.head is equal to null, and ret.tail is equal to null, and then return ret. So I guess we can just have the same functions here. So add, remove, get, and then free. So I'm actually just going to call, or no, I should not. I'm going to put it off this side just so I have the proper functions. So allocate, then we'll have a void dlist add, pass in a delinked list pointer list, and then a void pointer element. Then a void dlist remove at idx, delinked list pointer list, and void pointer element. And then it's pretty common for lists to have a remove first and remove last, especially with linked lists. So we'll also implement those. Void dlist remove first, delinked list pointer list, void pointer element, and I should actually be returning pointers here in the remove methods at least. And then void pointer return dlist remove last. And then the same parameters. Or actually, for remove first, the parameter, it should only have just the list parameter, and for the remove at idx, the second parameter should be an unsigned integer idx. Then we'll have a get, so void pointer get, and we'll pass, or dlist underscore get, and we'll pass in an unsigned integer idx, and then free and free deep. Once again, so void dlist free, pass in a delinked list, and then a void dlist free deep, pass in delinked list. And then I forgot to, for the get method, have a delinked list pointer as a parameter, because we need to get the element from the index. And what we could also do here is have a visit method, or you know, I'm not gonna do that right now. Alright, so I'm gonna copy the rest of these definitions over, and we'll start with dlist add. Or we should actually add two more methods here. So add will be renamed to add last. Then we also want to have a void dlist add first, delinked list pointer list, and void pointer element, and then void dlist add at idx delinked list void pointer element. So make sure that you have the rest of these in here. So we'll start with add last because it's the simplest. So for add last, we essentially have to take the tail, and since it has a pointer to the next element, which is usually null, we're going to say the tail will be, it will just point to the element that we want to add. Now, the conditions will get really tricky here. So what usually happens is in the doubly linked list is instead of having actual elements at the head and tail, is we have dummy elements, so kind of cushions per se. So let me actually, if I can find a picture of this somewhere. Double linked list dummy elements. I don't know if this is an actual thing, but yeah. So essentially, we just have elements here that will always be there, but they won't ever be accessed with indexes or with that, or you can't deallocate them. They're always going to be allocated. The values, so the void pointer values will be just null, and then when we first allocate, they will both point to each other. So for allocate, instead, we have to have a few things here. So ret.head is equal to malloc size of, is it dnode? Yeah, dnode. And then we should actually have a method to allocate a node here, real quick. So dnode, dlist, allocate node. And we'll pass in a void pointer val. So we'll just copy that signature in here. So for the allocate node, we essentially just create dnode ret, then ret.next is equal to null, and ret.previous is equal to null, and then ret.value is equal to val. So whatever the parameter was, and then return ret. Now for dlist allocate, what we're going to say is ret.head is equal to this is going to be weird. I guess because we can't just say ret.head is equal to the reference of the return value, because we can't take the reference of our return value, and if we were to assign it to a local variable, that local variable would be deallocated at the end. So what we have to do is create another function here. If you can tell, I did not prepare any code here. I'm just winging this. So dnode, return type dnode pointer, or actually, we will return a void dlist allocate node pointer, and we'll pass in a void pointer val. For this function, this will, or wait, sorry, we need to pass in a delinked list pointer. You know what? Well, we will return a dnode pointer here from this method. So this function will have to return a dnode pointer. So we have to initialize the div. So dnode pointer ret is equal to malloc size of dnode. Then ret.next is equal to null. Ret.previous is equal to null. And ret.value is equal to val. And then return ret. So it's pretty much the same thing, except we're explicitly allocating the memory here. And the reason why is, once again, because if we explicitly allocate the memory itself, it will be allocated not locally, or the pointer will be local, but the value itself will be in the heap, I believe. Yeah, it will be in the heap. So now what we can say is just ret.head in the dlist allocate. Ret.head is equal to dlist underscore allocate node pointer and pass in null as the value. And then ret.tail is equal to the same thing. Dlist allocate node pointer null, and then once again, since they're the dummy head and tail, ret.head.next will equal ret.tail, and then ret.tail.previous will equal ret.prev, or ret.head, sorry, just like that. Alright, so once again, we're just creating a dummy header and dummy tail here, because it just makes it simpler to actually do the operations on. Oh, this was not what I was looking for. This is what I was looking for. Alright, so now we can do the functions. So for add last, if we wanted to insert an element before the tail here, what we're gonna have to do is essentially take the pointer, or the last element, the current last element, and have it point to the new element as its next element, and then the tail will then point to the new element as its previous. So what we're going to say is dnode pointer new node is equal to dlist underscore allocate node pointer, pass in the element as the value, and then we're going to update pointers here. So list dot tail dot prev. So this is getting the current last element, and then that dot next is equal to new node. And then what we also have to say, or it doesn't like this. And then we also have to say new node dot previous is equal to list dot tail dot prev. Because remember, we have to update pointers in both ways. And then for the or is it the other, or then we also have to have it point to the have the tail and the new element point to each other. So list dot tail dot prev is equal to new node, and then new node dot next is equal to list dot tail. And notice how it doesn't matter if there's no elements in the table or in the list, because we have dummy elements there. If there weren't any, we would have complex conditions about when we would just set the header to the new node, when we would set the tail to the new node, and stuff like that. So it would be a clusterfuck essentially. But it's just the dummy nodes make it easier. Alright, so that's add last. Add first will be similar. So we'll similarly allocate a new node. So dnode pointer new node is equal to dlist underscore allocate node pointer, passing the element as the value, and then update the pointers. So list dot head dot next dot previous is equal to new node, because the current head, or so the current first element, not the dummy head, will have to point to the new node in its previous. So the previous value of the current head will have to be the new node. And then we'll have to say new node.next is equal to list.head.next. And then list.head.next is equal to new node, and new node.previous is equal to head. Just like that. And then for adding an index, it's going to be a little similar here. Oh, but we forgot to actually add the index as a pointer, or as a value parameter. So we just have to add this as the value here. So if idx is greater than or equal to size, just return, because you didn't add it, or is greater than or equal to list.size. Then we have to essentially iterate through each element until we get to that index. So now this is where the efficiency of, or some of the drawbacks of a linked list are, because all of the insertion methods for the dynamically sized list will be constant unless you have to resize, but because we're doubling the size, that will only happen, especially when we get into large fat ass lists, that will be called less and less. So now we're going to have to do this and iterate. So for unsigned int I is equal to 0, I is less than idx, I plus plus. And then we also have to, since there's no array structure, so we can't access stuff at an index, what we have to say is, we essentially have to have a parallel loop here that, or another value that we have to increment through. I can actually, what we should actually do is have, I want to have a value or a function that takes a function pointer and visits a node at an index. You know, what we can actually do is just have a function to return the pointer. So node pointer, or dnode pointer, dlist underscore get node, pass in a dlinked list, and then unsigned integer idx. Yeah, so this will just make it easier. So for get node, we will have the boundary conditions in there actually. So if, oh, I forgot the unsigned integer. That was a mistake. So if idx is greater than or equal to list.size, return null. And then otherwise we're going to have a loop here. So for, and then we're going to have two initial conditions, or two initial statements. Unsigned int I is equal to 0, that's pretty standard. And then a comma, then we're going to have a dnode pointer, current is equal to list.head. The reason why is because, once again, we can't access stuff with an array, so we just have to count the number of times that we're accessing the next element. And then for the condition, I is less than idx. And then for the increment statement, I plus plus, comma, cur is equal to current.next. It doesn't like this. Oh wait, I don't think I can do this actually, because you can't define two elements in the starting condition of a for loop if they're not the same type. So yeah, I was trying to be cool, but we can't. So we just have to remove the node declaration outside of the for loop. So it just becomes I goes from I to idx, or from 0 to idx, and then I++ for the increment. And then inside the for loop, what we have to say is just cur is equal to cur.next. And then just as a safeguard for the condition, we will say I is less than idx and cur.next. Because if current.next does not exist, if it's null, then there's either we fucked up, the code fucked up, or I mean, I think that's the only way, because there's already an index condition out here. And then we essentially just return cur. So if we were to look at this image here, index, and we started I at 0, and let's say we wanted to get index 1, so that would be the 7 here. I should actually, let me just do this in the loop, or in the... I'm just gonna draw this out, because it's a lot easier to explain rather than you having to follow my cursor. Alright, so let me copy this image over. So I'm gonna have an IDX here, and then also an I. So the 4 is at IDX 0, and the 7 is at IDX 1. That's in the list. I will be the counter that we're using here. So we start at IDX I0. And then 0 is less than 1, which is good, so we go... I think we have to make this condition I is less than or equal to IDX. I think. Yeah. Yeah, it has to be less than or equal to. So I is 0, and then we go next. So this is the current here, and then when I is 1, we're still good on the comparison, and then we go to 2. So I plus, fuck, is this gonna work? I think we have to start current at list.head.next. Yeah, that makes sense. And then the condition will be I is less than IDX, not less than or equal to. Yeah, so that makes a little more sense. So we start I at 0 with the head.next. So this is head next. So we start at the 4. Then we just say current is equal to the current.next, so that gets us here. Increment I to 1, and 1 is not less than 1, so we return current. If it was larger, same concept would apply. Okay, so in the add at index, we're gonna have a we're gonna use this node now. So this node is actually all we need, because we only need to update the pointers in the surrounding nodes. So dnode pointer cur is equal to get or dlist underscore get node, pass in the list, and the index is IDX. And then if not cur, return nothing. just return, because we can't, because this boundary condition failed, so we're just return null. So not cur would evaluate to true. And then now what we have to do is something similar to first and add last, because we're updating the pointers around the current node. So when we're inserting, we are inserting at the index, so everything will essentially have to be right shifted beyond it. This is pretty similar to the dynamic array, so we just have to right shift everything essentially. So how do I want to say this? So we'll start by doing current dot, or we have to do this, we have to be careful here. So we have to allocate a node here. So dnode pointer new node is equal to dlist underscore allocate node pointer, and then pass in the element that you want to insert. And then new node dot previous is equal to current dot previous. Then current dot previous dot next is equal to new node. So note the patterns here. So whenever we set the previous to a node, then we have to set that node, that node's next to the other node. So it's a linked relationship here. So if we insert the 7, we have to say the 7's previous is 4 and the 4's next is 7. And then on the other side, we have to say new node dot next is equal to current, and current dot previous is equal to new node. Yeah. So just like the other add methods, we have to update 4 pointers. And this is essentially updating 2 groups of pointers, because once again, if you update one pointer, you have to update the other pointer that is in that group. So let's test these. So I'll include in the main file, include delinked list, and I think I added it to the build path. I did. Alright, so we'll have another character array. And then I also want to have a print method here, so void print char dlist, and pass in a delinked list pointer list. And what we're going to say is we're going to do something similar to the get node. However, if we were to call get node every time we wanted to iterate or visit a node, what would happen is this would essentially call this method every time, which runs an O of n, and because we're running that loop O of n times, that would be O of n squared. However, if we had something similar with the pointer here, and we just called visit node or something like that on one of these, then we would what we can do here is we can use function pointers. So I need to refresh my memory on the syntax here. So give me 2 seconds. So in delinked list.h, we'll define another function here that will be void, and it will be dlist underscore visit node. Pass in or no, actually we're going to have a dlist iterate. This is going to be a function iterate. Pass in a delinked list, pointer list, and then we will pass in a function pointer that will be called at each element. So the syntax here is return type, so void, and the name, so visit, and then that in parentheses with an asterisk here, so that's the syntax there. And then after that we have another set of parentheses with the parameters, so void pointer element. So I'll copy this signature. And it's going to be pretty similar to get node here. So we'll say dnode pointer current is equal to list.head.next. And then this time we're going to have a while loop. So because it's just simpler, we don't need to have any, we could put this in a for loop, but the thing is let's be cool and let's put it in a for loop. So for dnode pointer current is equal to list.head.next. Current is just the current.next because that's a pointer, and if it exists it will evaluate to true, otherwise it will evaluate to false. So if it's the tail, so if there are no elements in the list, list.head.next is just the dummy tail, and dummy tail does not have any next, so this will evaluate to false. And then the incremental step here will just be current is equal to current.next. Once again, pretty similar to the for loop above. And then in the body we'll just call visit, so call the function pointer and pass in current.val. Yeah, so that's pretty simple there, but this is an interesting structure for the for loop. It's not too common that you would see something like this. Now for what we can do is for the method in main.c is it will take in now a void pointer element, and then all we have to say is just printf %c comma and then space, and then just pass in a dereference, and then in two sets of parentheses character pointer, because we want to convert the pointer, so we want to convert element to a character pointer and then dereference that pointer, and just print that. And then I'll have another function here that just says void print char dlist and pass in a delinked list pointer list. And what this will do is just call dlist underscore iterate, and we will pass in the list, and the function pointer will just be print char dnode. I just changed the name there. So those are the two functions in main, and then now in the main function in main.c, we will have a for loop. It's for unsigned int I is equal to 0, I is less than 5, I plus plus. We're going to add all the elements here. So we actually have to allocate the doubly linked list. So delinked list is equal to allocate dlist allocate. That's it. We don't have to pass in any parameters because there's no default. There's no capacity. Then what we're going to say is list or dlist underscore add last, pass in the list, and then the element will be r plus I once again. So this is just what we had last time. And then I will print out print char dlist and pass in a reference to list. Ooh, this the add last also has to take in a reference to list. All right, let's run this. Okay. Doesn't like this. Yeah, okay. So I thought this would arise. So in the dnode structure, we're trying to access something called dnode, but it doesn't know what dnode is yet. So what we have to do is change the structure definition. So I'm just gonna redefine it. So we'll just have struct dnode, and then in the curly braces we will have the void pointer value, and then struct dnode pointer next, and struct dnode pointer previous, and then after the braces put a semicolon, and then we have to do a type def separately. So type def struct dnode, and now it should recognize everything. Just like that. Oh, missed. Alright, now let's run it. Still didn't like something. Did I fuck something up here? Dynamic array 7. Why is it over there? Oh, because, oh, right, yeah. Alright, so in dynamic array, when I added all the tags, I didn't update our calls to them. So just make sure that if you update the names to the functions, that you actually call those new names inside of the functions. I think that should be good. So now let's run it. A, B, C, D, E. Perfect. That's all the elements, and now let's try adding some new things. So we'll say add, or dlist underscore add first. Reference to list. Oh, I need to fuck. I'll just have a few more values here to add. And then this will be r plus 5. dlist add at idx. Reference to list, and then r plus 6, and we'll insert it at index 3. And I'll print the list at each step. Oh, you know what I didn't do? Is I didn't update the size for any of these things. Yeah, so for delinked list, for all the adding methods, make sure that you increase the size. So list.size ++. Yeah, make sure that you don't forget to do that. So now if I run, oop, I need to print an end line at the end. Okay, so A, B, C, D, E is the initial. Then we add F in the front, so F, A, B, C, D, E. And then we add at index 3, so 0, 1, 2, 3. The elementary G, so F, A, B, G, C, D, E. All right, perfect. So I guess we just have the removal and free methods now. Let's actually do the get method first. So for get, we can actually just say dnode cur is equal to dlist underscore get node, passing the list and the ID and the index, and because that will just get the node at the index, which is, and then we just want to return the value. But if, and then we can just say, do a ternary operator here actually. So return current as the boolean, and if current is true, then cur dot val, otherwise return null. Because if current is null, then it doesn't have a value. That will definitely work. Alright, so remove first, or let's actually do remove last, actually. Remove last is kind of the opposite of add last in terms of the pointers. So let's get the return value. So void pointer, or let's say a dnode pointer, ret is equal to list.tail.previous, because the previous element of the tail is the last element. And then if not ret, return null. That's just a boundary condition, so... Oh, wait, that's never gonna happen, actually. Damn, can you guys hear that fucking siren? Give me a second, let me... God, imagine if we didn't have any emergency services. That would just make my videos so much quieter. I don't care about the other consequences. That's just all I care about is me having a quiet spot, because it's just so bothersome. Okay, this is this the last song in the oh, it is the last song. This lasted a bit longer than I thought it would, but then again, kind of did, I was not prepared enough for this, I do admit. Alright, let's get back to it. I think the fire truck is gone. Alright, so return the node ret will always have a thing. So that if statement was actually that if statement did not matter at all. So what we're going to say now is ooh, I actually do. This is going to be interesting. So we delete that actually. Or wait, no, leave that there. But we're gonna have to. I keep jumping around all over the place. But let's have a free node method, just like we had an allocate node. So void free node and pass in a dnode or dlist underscore free node. Pass in a dnode pointer node. Or wait, do we? Fuck. Shit, this is gonna be. God damn it. And then we'll also have a second method here, void dlist underscore free node deep. Pass in dnode pointer node. Alright, so these are two new methods. God, I'm sorry, this was not planned at all. So for free node, all we want to do is just free up the memory. So free node, that's all. For free node deep, however, we want to free up the memory inside the node as well. So node or free node dot val, and then just free node, just like that. Now we can actually do the removal method. So remove last. What we're going to say is ret.next.previous is equal to ret.previous. So now, let's say if we were to remove the 7 here, we would essentially just have to link the 4 and the dummy tail together. And then ret.previous.next is equal to ret.next. And do we have to do anything else actually? No, this is the only thing we have to do. Or wait, is it? Yeah, this is the only thing we have to do actually. Because if we were to, when we add an element, we have to update 2 sets of pointers. But now that we're removing something, we only have to update 1 set of pointers. And then we free the node. Or we actually have to get the void pointer return value. So I'll rename the node, the current node, just to cur. And then the void pointer ret is equal to cur dot val. And then if, or not if, we're going to say free node, delist free node, and pass in current, and then return ret. Just like that. And then for remove first, it's going to be something very similar actually. You can actually just copy the code over, because the whole remove, the updating pointers will be the same, except dnode cur will have to be list dot head dot next. And then for removal at index, we're going to do something similar to add at index, where we have to get the node. So dnode pointer current is equal to list or dlist underscore get node, pass in the list and the index, and then if not cur, return null. Just gonna do something quickly. Just gonna rearrange some of this so it looks a little better. All right, so if the node does not exist, so if the index is either too large, yeah, if that's all it is. If the index is too large, it's gonna be null. And then then we have to update the pointers around it. So cur dot previous dot next is equal to current dot next, and then current dot next dot previous is equal to current dot previous. Right? Perfect. And then we also have to get the element, so void pointer ret is equal to current dot val. Ooh, this should or no, that we're fine. And then return ret. Ooh, actually, we do need boundary conditions for the remove first and remove last, because if the size is 0, then list.head.next will be the tail, and that's current, but current, which is the tail.next, will be null. So we'll get a null pointer exception. So just to avoid that, we have to have a boundary condition. So if list.size is equal to 0, return null, and then copy that if statement for the remove last. Just like that. And then we just have 2 more methods, free and free deep. All right, so for free, what we will do is we'll kind of do something similar to the traversal. I don't think lambda functions are a thing in C. I actually don't. Let me check lambda function. I think this is completely, yeah, lambda expressions is only in C++. Ooh. Ooh, simple macro, yeah. Actually, ooh, what about this? In dlist free, ooh, wait, no. Wait, would that work? No, it would not work. Okay. So for dlist free, you can copy the loop from iterate, and then inside the body, just delete, have an empty body now. So just delete the visit call, and then we have to say free, just dlist underscore free node, and pass in, or wait, since it's, oh, wait, shit. Okay, this is going to be a little weird because we have to maintain pointers to the next thing, but if we free the current node, then current.next is nothing because current is null. Alright, how about this? dnode pointer current is equal to list.head.next, then while current.next, ooh, shit, oh yeah, while current.next, then we just say, or wait, we can start current at head, and then we free the current, so free dlist underscore free node current, and that will be the head, and then, or we have to call something first. Current is equal to current.next, and then we call free node on current.previous. And then we have to call free node on the tail. So dlist free node current or list dot tail. So let me draw this out actually. So let's say we have that one, two, and then three. And then the dummy tail. So we start current here. And then what we say is current is equal to current.next. So we go to the next element, which is this. I didn't put any of these in here. So the current is this, and then we go to the next node, so the one, and then we just free the memory in the current, or in the previous one, which was that one. Then we're over here, go to the next and free the previous, which is the 1. And now we're at 2. Go to the 3. So we're at 3, and then free the previous, which is the 2. Then go to the dummy tail and free the previous, which is the 3. And then now after the loop, we just free the tail when current.next no longer exists. Alright, so that's how that works. Now for free deep, you can essentially just copy the template from free and then just replace calls to free node with free node deep. And I think that should be good. Yeah, I'm not really in the mood to test this. This is taking a lot longer than I wanted it to. But yeah, you guys can test this on your own. I'm not even checking for errors, but I definitely will in a second once I'm done with the stream. But yeah, so that's generic lists in C. And a really cool thing about this is, since it's a void pointer, you can use this for any type of pointer. It doesn't matter, really. You can have an integer pointer, you can have a structure pointer, you can have a double pointer. And this will be helpful if you want to use it for something where you need that dynamic, like a dynamic type. So I was thinking of, the reason why I wanted to do this was to actually implement this with JSON and file reading there. So this would be super helpful on that end. Because I was thinking about changing the way that the JSON library worked. So yeah, that is pretty much all I had to say about linked lists and dynamically sized arrays. Once again, the biggest difference was just how you represented the nodes, and one thing I didn't really talk about was how much more memory the doubly linked lists take up. They take up 3 times as much memory, because each node in the dynamically sized array is just a void pointer value. However, in each node for the doubly linked list, it has a void pointer value and then 2 pointers for the next node and the previous node. However, with removal, it's all of these methods here, the removal and addition methods, those are all constant time. There's no shifting required or resizing required at all. However, once again, with larger lists, array lists do help because you're not usually, when you look at larger lists, you're looking at data. So you're not going to be removing, you're just going to be adding. But the thing is, here, accessing takes O of n, which is the biggest downturn because most of the time you're going to be accessing elements of a list. And if that takes O of n, that can really be taxing on a list or on your runtime. So yeah, that's pretty much all I wanted to say there. Hope you guys enjoyed. I am definitely going to do shadow, or I'm not going to say definitely, but I am planning on doing OpenGL shadows over the weekend. Just getting that over with, just because I've pushed that off for however long. Yeah, hope you guys found this informative, and I think I'm going to do something similar with generic hash maps and hash sets, just once again so I can use this for JSON or something, but that's just my plan there. A little bit of a more conceptual, less math intensive programming challenge. I mean, for the most part, a lot of these challenges have been more math intensive. I mean, we've done, let me see, this is the 22nd, I believe. And yeah, we've done a bunch of shunting yard stuff, which is both computer science but it also has math, Dijkstra's algorithm math, RSA math, Shunting yard again. Number bases, that's kind of math. Perlin noise, also math. So this is more of a conceptual one, but it's also very procedural, which is cool. So yeah, hope you guys enjoyed, and I'll see you guys this weekend or next week. And yeah, I'll see you then. Have a good one.